Hello and welcome back to week 2 of this course. Before we start anything new, I would like to give you a rather quick review of what we studied in the first week. That basically boils down to two forms of interest. The first one is called simple interest. The other one is compound interest. Okay. The definition of those two can be given by the form of account value, so accumulated account value. So if you are in the simple interest, it is given by this form. So here X is called the principal, or it's rather the starting value of your account, because when you plug in t equals 0, you get AV0 equals X. So that is the starting point of your account. And as time t moves forward, your account value is AVT. That is how your account value grows. And it's obviously it's a linear function, right? Because it's in a linear form with slope t, right? For the compound interest, if it is compounded once a year, it is given by this form, right? And we also learned compound more than once a year, right? So here we can assume the compounding frequency is m times a year. If m equals 1, that means you receive interest once a year. If m is 2, you receive interest twice a year, so it's semi-annually. So in this more general form, we have AVT equals x times 1 plus I. So here for the notation purpose, we will put a superscript to denote this is the nominal rate compounded m times a year. So here is nothing but a special case when m is 1, okay? So this is the definition of both simple and compound interest rate. And we also know that in this case, in the simple interest rate, this is a constant, right? So the amount of interest accumulated over any given year or any given unit period is a constant. Here is the rate. So it's not exactly the, so I use percentage to denote. The rate is constant. So that is rather the key difference between those two forms, okay? Once we know how they accumulate, we also studied a special case when m goes to infinity, right? And that's somehow what we will learn is the continuous force of interest. Okay, so the most important thing obviously is the definition of simple and compound interest, and the most important feature. So for the simple interest, it's the difference or the accumulated amount, over any single period is constant. Here in the compound interest case, it's the percentage. It's a constant. So now let's start something new. It's section 4 is accumulated value. Okay. Technically speaking, this is not new because we already know what the accumulated value is when we define simple interest and compound interest. Okay, so let's take a look at the definition. Again, here we separate the definition into two cases, right? So there's the case of compound interest and there's the case of simple interest. Comparing to what I just wrote, basically here we just normalize, right? So we set this to be 1. Okay. Sometimes I may also use the word normalization or normalize, right? Because this is essentially the definition of simple or compound interest rate, except that there's no longer x because I set x to 1. So basically I start with $1. I want to see how my account grows at different forms of interest, right? So here we study simple interest and compound interest. And here we put a name. We call it the accumulated value factor. So this is the factor. So that's why here there's another letter F. F stands for factor. So here we have AVF, that is accumulated value factor. So whenever you have a different principal, say my X now is not 1, it's 10. All I need to do is, so let's now assume my account value at the beginning is, well, let's put 100. So $100 at the beginning, okay? So if I want to know my account value or accumulated value at any time t, all I need to do is to use my initial value times the factor. So basically, once we have AVF, we can easily get to any AV for any X. So that's rather simple, okay? An important thing I want to note is here, money has time value. Okay, so that means $1 today is different from $1 tomorrow. In most cases, we would say $1 today is actually worth more than $1 tomorrow, because according to the definition of AVF, the account value actually grows, right? Sometimes maybe along a straight line, sometimes maybe grows a lot steeper, right, as in the compound interest rate case. So I put here that we are greedy, so we would prefer $2 tomorrow today to $1 today. So in order to compare later on, we will compare which strategy is better or which strategy is the best among all. We would need to convert all the account values to the same time point here. So that is very, very important for this course, because whenever you are doing comparison, between two different accounts, you must do the comparison at the same time. Okay, so you cannot compare, say, account 1 at time 1 to account 2 at time 2. Okay, so that's not how things work. We must make sure the time is the same for different accounts. Then we can do the comparison. Otherwise, given that money has time value, right? So it's not surprised that two accounts are different at different times. Even the same account is different, right? So that's the remark I would like to mention. Now let's do some examples. The first example is 1.8. So if you have the textbook, please go to page 10. Example 1.8. So I'm going to read the question. A deposit of $100 is invested today. Another $100 is invested at the end of 5 years using an annual simple interest rate of 6%. How much is this investment worth at the end of 10 years? Okay, so as usual, okay, for this chapter or even for most chapters of this course, it would be really, really helpful to draw a timeline. Okay, and along this or on this timeline, we're going to make marks of important transactions. So today, let's say today is time 0. Okay, so I assign t equals 0 for today. Today I deposit. Okay, so I deposit $100 today. And also I'm going to make another deposit at the end of 5 years. Another deposit. Okay, so here I put arrow down to denote this is money in. I use arrow up, to denote is money out, but it's your preference, right? So if you put the amount underneath, that's going to be arrow up, right? So basically the direction of the arrow goes to the timeline. That means that is money into the account. If the arrow is away from the timeline, say in this way, that means it's money out of your account. Okay, so that's my personal preference. Of course, you are free to pick anything you like. So let me erase this. Oh, that's the highlighter. So let me erase everything down here. Okay, what we want to know is how much at this time is my investment worth. Okay, so here we have two deposits. Okay, so the first one, we need to calculate how much it is worth at the end of 10 years, right? And it is simple interest with I equals 6%. So basically, what I have done so far is to translate the information, the question, into somehow a mathematical format, right? So here I have a timeline denoting money in, money out, and then I write down the interest rate, and I put simple to denote this is actually simple interest rate per annual. So again, this is because at the very beginning, right, at this course, I'm trying to give you a workable strategy, for most questions. Okay, so now for the first investment, I plug in 1 plus ti. Okay, from time 0 to 10 years, that's 10 years, so equals 10. Right. So this is the amount of money I will be getting. Okay, by depositing $100 today, at the end of 10 years. Okay. And I did another deposit at the end of 5 years. So for this, I still have $100 deposit, but now from 5 to 10, the time in between is 5 years, right? So when I plug in the accumulated value formula for simple interest rate, I will need to plug in 5, okay? So basically here is T. For the first deposit, okay, the time span is 10 years. For the second deposit, the time span is 5 years, okay? So plug in, get a calculator to find out the final result, 1.9. Okay, so in this question, a deposit of X dollars is invested, okay? I don't know how much this X exactly is. At time 6 years, at an annual effective interest rate of 8%. A second deposit of another X is invested at time 8 years at the same investment, at the same interest rate. At time 11 years, the accumulated amount of the investment is 976, calculate X. So this is very similar to question 1.8, except we know the end value. Okay, so here it's not 10, here it's 11, but we don't know the initial deposit. So again, let's draw timeline. Okay, my first deposit is made at time 6, so t equals 6. I made the first deposit of X dollars. Okay, and then I made another deposit at 8 years, another deposit of same amount. Okay, at time 11 years, the account value is 976. So this is how much this is worth, which means if I withdraw everything from this account, I will be getting $900.76. Okay. We repeat the same thing, right? So here, the first deposit goes from, by the way, the interest rate is 8%. So all we need to do is to figure out how many years, right? So here from 6, the end of 6 to the end of 11, that's 5 years. And here we have compound interest rate. Okay, because it says it's the annual effective interest rate, and let's assume it's compound, because usually that's the default meaning. If the question says it's simple interest, so you use simple interest. Otherwise, you just assume it's compound. Okay, so the interest rate is 8%. The first investment spans for 5 years, from 6 to 11. Okay, sometimes you may wonder why it is 5 years, not 6. Okay, if you are not convinced, you can do this, right, at the beginning, right? So it doesn't hurt. right? So let's draw it down, okay? So let's count. Year 1, year 2, year 3, year 4, year 5, right? So it's exactly 5 years. So all you need to do is to use the end time minus the starting time, okay? But pay attention to the wording. Sometimes, so usually the default setup is the end of the years, okay? Sometimes they may say it's the beginning of the year. So you have to be careful because say here in 1.8, okay, I say I make the deposit today, okay, so it's the same as to say I deposit the money at the beginning of the first year rather than the end, right? So if I make the deposit at the end of the year, it will be here, but I do the deposit at the beginning, so it's at time 0. So just to be careful. So the second deposit accumulates at the same 8%, but now I only have 3 years, right? I know at the end this is 976, because what I'm doing is actually converting the amount of value or the amount of money from different time to the same time, which is 11 years. So if I use a different color, let me demonstrate that. So what I'm doing here is to convert this amount to time point at 11, okay? And the second one, let's try this color. So the second one, what I'm doing is to convert this amount to 11, right? And then all 3 values are at time 11. So this goes to t equals 11. This goes to t equals 11. This is already at 11, right? Because that's what question tells us. At time 11, at the end of 11 years, the amount is 976. So now all 3 of them are at t equals 11. So we can do basic addition, basic subtraction, because they are at the same time. So that's the key point, right? So you should be able to solve this, right, to get the result. How about I change the question a little? So at the end of 8 years, I didn't deposit X dollars, okay? I instead doubled the investment. Repeat the question, okay? So still assume that at the end of 11 years, the account is worth of 976. Now, what is X? Okay, so think about that question. Finally, 1.10. Jim invests 500 at the beginning of 2002, 2003, and 2004 in a bank account that pays simple interest. At the end of 2004, the accumulated value of the account is $1,635. Calculate the rate of interest. Okay, so that is the third type of question, right? 1.8 asks you the terminal amount of your terminal value of your account. 1.9 asks the amount you deposit at the beginning. 1.10 asks the interest rate. Okay, so let's repeat the same procedure. So here is 2002, 2003, here's 2004. Okay, Jim invests 500 at the beginning. So here at the beginning, I have 500. So this 500 is for 2002. Okay, let me use different color. Okay, my second one is for 2003. So let me also use the same color. So here is for 2003. Okay, so this second deposit, the third deposit is at the beginning of 2004. So this refers to the deposit at the beginning of 500, not 2004. So here is 500. Now what do we have? At the end of 2004, at the end, the accumulated value, so let's say I withdraw, I will be getting 1,635. Okay, so here are all the notations. Okay, maybe I should pick a more contrasting color for the final one, but anyway, that's the setup. I want to know the simple interest. By the way, here the value accumulates at simple interest rate. I just don't know at what rate. So let's do the calculation, okay? So my first 500, how many years, right? We can count 1, 2, 3, right? 3 years. So the 1 plus TI, 3I, okay? My next one is blue. I mean, I should use blue. My second one, the 1 plus 2I, okay? My last one, I somehow forgot which one I picked. Hopefully this is the color. 500, okay? For the last deposit, it only lasts for 1 year, right? Okay, so finally, I'm going to equate all of them to 1,635 because now all of them are at the same time at the end of 2004, right? So I can do the computation. So this is actually 4.5%. The more complicated case is for the compound interest rate because in that case, you will not be able to get explicit result. For instance, if we try the same question, but for compound interest rate, what will be happening? So this is my first, the value of my first deposit at the end of 2004. Then I have my second. Then finally, I have my last one. Okay, and solving this equation is obviously not trivial, right? I'm not sure your calculator has the built-in function to calculate or not, but in case I do ask you this question, what are you going to do? Okay, obviously it's very difficult to solve this question, right? It's a polynomial in the third order. Well, technically you can solve, but it's too complicated, right? So one possible way is to try, or rather say trial and error. Right? Usually you have multiple choice questions, right? There are 5 of them. All you need to do is to plug in, right? So once you plug in, it's very easy to check, right? So let's say you can check I equals 4% to see whether it equals the right-hand side or not, and to try all 5 options, and one of them will give you the best result, the closest one to the right-hand side. That would be your answer, okay? Occasionally, SOA will give you a question like that, but it's not that common. So that's for this section. Now let's move on to talk about the next present value. It's rather close to what we just did, except we reverse the time. We do not convert time value, into future, but rather we look backwards. Okay, we discount value from future to present. So that's why this section is called present value. So if you look at definition 6, it's pretty much what we have, before, except now we do discounting, right? Remember, what we used to have is, so assuming compound interest rate, right? So X is the starting value. So here in this graph, here's 0, here's T. Here is X, here is AVT. Okay, now we are doing something different. Well, not that different. It's reversing the timeline. So now what do we have? At time t, I have X dollars. Okay, I want to know how much is this X dollars worth at time 0. So I discount back, right? So this is PVT. So there is a little confusion of notation, right? Because here t is not exactly the time at t, right? It's actually time at 0. So it's the present value of X amount that is at time t, okay? So I want to discount it back. So here I'm basically following the notation of the textbook. Personally, this is not what I usually do. Usually I will put PV0 because so my personal. But please follow the textbook notation, okay? My personal notation usually is to write this as PV0, okay? But I treat PVT as X. So I discount back so that I know how I'm tracking, but we do not use this, okay? So I simply follow the textbook to make sure we are on the same page, okay? So basically that's how we define it, or rather I can give you a different view. That is, let me get additional page. This is one of the most important arguments in modern finance. So let's do this. Okay, why this is the definition for PV? This is the so-called no arbitrage, TARG, no arbitrage argument or no arbitrage opportunity. Okay, so we know. So assume compound interest rate. Okay. So here is time 0, here is time t. So assume here my account value is x. What would be the initial amount? So if we apply the accumulated value formula, what would be? X equals, so let's call it x0, shall we? So here is my initial value, I call it x0, is 1 plus I to t, right? So from this, I can solve for x0 is x divided by 1 plus I t. Okay, so now assume my present value t of x is not this. Well, if it's not, there are only two options, right? So the first option is this is bigger. Okay, so if this is bigger, what's going to happen? So I'm going to if we can think this as something we can buy and sell, or we can think as borrow or lend. So I should lend out, okay, and borrow this amount. Okay, for this transaction, okay, what I will be getting is here's at time 0. Okay, at time t, let's do not use time. So let's just simply put 0. Okay, so this will become x. This will become pvt times 1 minus I to the t. Right? So so what we have is, right, because I have already assumed that. So so this strategy is going to create some kind of, you can think this as arbitrage, because between those two, this is overly priced, right? So you should sell something that is overly priced and buy something that is underpriced. So, but it's I'm not sure. Did I get the sign wrong for the borrow or buy, because it is slightly different? But anyway, the argument is it's very straightforward, right? So if this equality does not hold, then things are weird, because if you start with this, you do not end up with x, right? And that's not what we want, because according to this definition, I do have x dollars at time t. So it must be given by this form. So you can think this as well, either an independent definition or a result because of the AVF or AV definition. Okay. So of course, this is very straightforward, right? Once we consider simple interest rate. Okay, similar to AVF, we can also define a present value factor. There are a lot of notations. There are a lot of initials. So make sure you know the meaning of them. So here we are talking about the PV and the PVF. So basically, the only difference between PV and PVF is here your x is 1. Okay, so when you divide by something, it's just 1 divided by something instead of x dividing by something. This is often we may call it the 1-year discount factor. Okay, so this is often very, very helpful because in the future questions, we consider a lot more of compound interest. And with compound interest, once we define V, things become a lot easier when we do discounting, right? So with this, how am I going to discount $100 from, let's say, 5 years to 0? So here, according to this, my present value 5 will be, okay, so technically it will be 100 divided by 1 plus I to the power 5, right? With the introduction of V, it's ready, the formula becomes, nicer or neater, if you want to call it. So this is the reason why we introduced this 1-year discount factor, because it really, really helps us to do the computation. By the way, here does not need to be 5, right? So I can try 5.5. Oh, so the computation is very straightforward. But for the simple interest rate discounting, it's slightly more complicated because t goes inside the -1, right? So it's slightly more complicated than the compound interest rate when we do the discounting. So now let's do the examples. We have 2 examples on page 13, 1.11. A payment of $10 is to be made at time 7 years. Determine the present value of this payment at time 0 at time 4 years. The annual effective interest rate is 6%. Usually when you see like the annual effective interest rate, you can simply work with you should work with compound interest rate. So as usual, here, I know I have $10 at the end of 7 years. We need to figure out the discount rate for the time 0 and time 4. So basically we are doing the discounting. Okay, PV7, that means we want to discount this amount to time 0. So it's 10 divided by 1 plus I is 6% to the power of 7. Okay, so of course you can do this calculation first. Okay, you can compute, and then this is right. Okay, the next question asks you the present value at 0.4. So let's get blue. So to this, okay, here comes the a little bit fast of notation. So here the time span is 3 years, right? So here the subscript is 3 instead of 4, right? Because sometimes we often use the subscript for the corresponding time. Here time is 4, but the duration or the interval between those 2 time points is 4. Is 3, excuse me. So that's why here it's PV3. The computation is rather simple, so I will leave that to you to complete. Okay, the next one, a payment of 10 is made at time 7 years. Determine the present value of this payment at time 0 and at time 4. Now we work with simple interest rate of 6%. Okay, so I just do the first one. So basically, we just need to discount or divide by the AVF, accumulated value factor. Right. So of course, if for the next one, it's from 7 years to 2 to 4 years, so it will be PV3. Right. So it's rather simple. I will end here, and in the next video, we are going to focus on rate of discount. That is likely the most difficult section of this chapter. So stay tuned, and I will see you in the next video.